Logistic regression is commonly used to estimate the probability of an instance belonging to a particular class. Similar to linear regression, it computes a weighted sum of input features. However, unlike linear regression, its output is not a continuous range of values, but instead representing a probability between 0 and 1. To achieve this, logistic regression applies a sigmoid function to the weighted sum of features. This is logistic regression vectorized form. Let's leave the weighted sum for now and take a look at the sigmoid function shape. When t is less than 0, the model predicts negative, and when t is larger or equal to 0, the model predicts positive. The goal of training a logistic regression model is to find the optimal parameter theta that assigns the high probability to positive instance and low probability to negative instance. Let's first look at the cost function of logistic regression. This is a graph of cost function. For the positive instance, if the prediction p is close to 0, the cost function outputs a very large number. For a negative instance, if the prediction p is close to 1, the cost function also outputs a very large number. So the model has a large cost error when misclassifying the instance. We can rewrite the cost function as a 1 function. It looks complex, but if you take a closer look, it is exactly the same as the previous function. For the actual positive, yi equals to 1. This part equals to 0. For the actual negative, yi equals to 0. This part equals to 0, and the function left with this part. There is no closed form equation to calculate optimized theta, but the cost function is convex, so we can use gradient descent to find the global minimum. This is a partial derivative of the cost function with regard to jth theta. And this is the matrix derivative form. After we have this formula, we can use batch gradient descent, stochastic gradient descent, or mini-batch gradient descent to train a logistic regression model and get the optimized theta. Logistic regression library in sklearn provides the actual implementation. Let's first go to the document and get a brief overview. The penalty default uses L2 ridge. We discussed the regularization in a previous video. Similar to linear regression, we can add L1 or L2 regularization to the logistic regression. C parameter is the inverse of regularization strength alpha. Smaller values specify stronger regularization. Solver parameter default uses LBFGS. It converges faster than gradient descent. The mathematical details are not the scope of this video. Let's move to the practical example and use the iris flower dataset to test out the logistic regression. First, let's take a look at the dataset. There are 4 features in the dataset and 3 different targets represented by 0, 1, and 2. Our first task is use logistic regression to clarify Virginica or not Virginica by Panto with CM. We simply select the column from the data frame and convert it into a NumPy array. We can inspect this feature, and the feature values range between 0.1 and 2.5. We convert the target y into 0 and 1 to represent non-Virginica and Virginica. Then simply give the logistic regression X train and Y train. Now we have built the logistic classification model. We add another logistic regression with C equals to 1000. Remember, the higher C, the less regularization. We can plot the logistic function on a graph. Here, we create 1000 data points in between 0 and 3. Because the feature range is in between 0.1 and 2.5. The predictProb function returns each probability score for each data point in X new. As you can see, the function curve looks like this. The blue dot line is called the decision boundary. It helps us to better visualize logistic regression. Left of the decision boundary, our model predicts negative, and the right of the decision boundary, our model predicts positive. We can find the decision boundary by finding the first x whose y value is larger or equal to 0.5. In our case, the x is 1.65. The blue line is a less regularized logistic function. Let's look at the logistic function. In order to find the decision boundary, we need to find the x value which y probability is larger and equal to 0.5. So this part should be equal to 1, which means features times theta factor should be 0. If we have one feature in the function, the decision boundary should be equal to this. If we have two features in the function, the decision boundary should equal to this, and so on. By this way, we can use the theta value to calculate the decision boundary directly. Let's try another example. We will use two features this time, petal width as well as the petal length to predict whether the flower is Virginica. And we will use the above-mentioned formula to calculate the decision boundary. This part of code creates a mass grid on the graph. Those data points are stored in the xnew. yprob stores each probability from xnew. We can draw the contour lines to better visualize the yprob. The contour provided by the MATLAB library connects the same values as a line. As you can see, this part of the area, our model predicts higher than 0.9, and this part of area, our model predicts less than 0.15. The black dashed line is a decision boundary, which was calculated by the formula from what we have discussed. This is the end of our video. Thanks for watching. If you found this video interesting and learned something, please consider like and subscribe. See you in the next video.